break up that tablet, the more surface area, the more it should react as well. So we'll go ahead, we're gonna do dueling rockets here. I'm gonna get one rocket here, you'll take this one. What was your name, my friend? AJ. AJ, nice to meet you, AJ. Which actually, if you wanna go to the Fraggle Rock Show later, we have the main character named AJ as well, who we've seen on stage. So AJ, you can go ahead and break up the tablet as big or as small as you'd like to. And then our next experiment, our next variable is how much water we're gonna add into our rocket. So I'm gonna keep it simple, I'll be the control. I'm gonna go one whole tablet, keep it normal. And AJ's breaking up a good little bit. There's more surface area. So now, AJ, should we add a lot of water or a little bit of water to your rocket? Not sure. Well, I'll start off first with my whole tablet here. I'm going to add in a medium amount of water. But also notice right now, there's nothing happening. It's dry, ingredients are separate. But once you add in some water, you'll hear ignition sequence start. That's when they begin the chemical reaction on the launch pad. So my friend AJ, get ready to run. Do this first one here, put it upside down. And that pressure is building.
Whoa!
Oh, that was whoa? You haven't seen nothing yet, my friend AJ. Because now this one, we're gonna add in only a tiny bit of water, and that way there's more space for gas inside the build. So go ahead, put your lid on top, listen for that good seal. There it is, put it upside down, and now get ready to run. In 3, 2,
Whoa!
1. That's more like it, that's power. But you see, we're chasing pressure. So the more water there is, the less space there's for gas to build. And now, if you want to see a real big wow moment, remember, the more surface area, the faster and more it reacts. So now, we're gonna crush it into a powder. Don't tell anybody, this is a very good secret here. If you do more rockets, show them this trick, and you'll be the #1 highest one for sure. But you see, by increasing the surface area, we go ahead and pour this powder into our rocket here. And now I'm gonna quiz you, AJ. A lot of water or a little bit of water?
A little bit.
A little bit, that's exactly right. That's chasing after that pressure. So we're gonna go ahead and look at that powder going in. That's our fuel. You can also use Coke and Mentos at home if you want a really big rocket. But my friend, go ahead and just a little tiny bit of water. Do you want to create the seal? Look at that reaction already, right off the bat. Get that good click. You got good quick. In 3, 2, 1. And we have liftoff. That's very simple chemical reactions. All we're using is Alka-Seltzer, but these rockets here, liquid oxygen, liquid hydrogen. Give it a shot. It's the beauty of science. While that one is going, I'm gonna drop some more water into this one here as well.
Oh wait, it might.
I see it moving, I see it moving.
It might pop off, but I don't think it's gonna shoot.
While this one's building pressure, I'm gonna move this to the side because now it's time to work with some real cool stuff.
Ooh,
liquid nitrogen.
Oh, liquid nitrogen.
That's cold.
Our nitrogen, it comes from this dewar here. Do you know anything about it? Do you know if it's hot, if it's cold? Do you know how cold it is?
No.
Any crazy guesses?
Like -200 something?
Even colder. In Fahrenheit, even colder. In Celsius, you're about exactly right. In Celsius, it's -196 degrees Celsius, but in Fahrenheit, it's a cool -320 degrees Fahrenheit.
Wow.
So it's one of the coldest things on Earth. My friends, do you know, what do you call space money? Money in space, what's it called?
What's it called? What do you think it's called, AJ? What do you think it's called?
AJ, what do you think?
I don't know.
I'll tell you this, right behind you. Starbucks. Now, my friend, feel it. This is not cold at all, in fact. But this liquid right here, this is a different story. We'll talk about it in a little bit as well, in terms of how you can touch it and get hands-on. But there is one very important rule also. This is a NASA rule. Anytime I'm pouring it back and forth, everyone here must go, ooh and ah. It's not my rule, I apologize, people. My friends, get your oohs and ahs ready. Ooh. Ah. Now, of course, we are working with liquid nitrogen, but you see all this vapor, all this gas coming off of it? That's because it's so cold that when it meets the air, it cannot, as a liquid, it starts to boil. Now, typically, boiling is very hot, of course, right? Boiling is just liquid going from boiling is the process which liquid goes from liquid to gas, but our nitrogen boils as soon as it meets the air around us. And just for reference, this is -320. When that meets the beautiful air around us, it's like putting your hand on a stovetop. That's how nitrogen feels. I'll add some more heat to it here in a second. But AJ, if I could have you take one big step back from my friend, because now I brought my pet snake to work. Is anyone afraid of snakes? No one's afraid of snakes?
Grandma.
Grandma? Well, my friends, the thing about my pet snake is he's not very smart, and in fact, he's a total airhead. My friends. You see, inside of our balloon, there is air, there is gas, And gas is always expanding. But what do you think is going to happen to it at negative 320 degrees Fahrenheit?
Pop.
Pop, we always think pop, or we all thinking pop?
Expand.
Expand. My friends, keep your eyes on our balloon here, because all these molecules react just like we do. When you're cold, you don't spread out.
Oh yeah, you get little.
You start to come together, you get little. All of these gas molecules are losing energy, they're losing temperature, and they're slowing down coming together. But the thing is, we haven't lost any air. Every single last molecule still inside of our balloon is just so cold, it changed its matter, so now we have liquid air at the very bottom. But not for long, because once it comes out of the air around us, it regains all that heat. Uh-oh, traffic jam. Be careful, my friend. There it is. It regains all the heat and it boils back to life.
Is that like frozen?
It's not quite frozen. There's some condensation at the bottom there. It's so cold that it condensates the air around us. But you see, I also want to say this one more time, because every single one of these rockets use liquid forms of gases like we are. You get a lot more of the gas in liquid form, but it's also much easier to transport. Liquids all stay together as one unit. But I'll show you one last time. That entire balloon full of gas only takes up a fraction amount of space in liquid form. But like we said, not for long. Once it comes out into the air around us, regains all the heat, a little puddle of liquid air at the bottom. And once it comes out into the air, don't touch that part down there, not that other part. The liquid oxygen about negative 297 degrees Fahrenheit. So it's still very cold. Not to mention very flammable as well, liquid oxygen. But now, my friend, let's see, for our next experiment, I'm gonna do you a favor. Once this lid is closed, you are going up. All right, do you think it's gonna work?
No.
Any ideas why it keeps popping off?
Because of the pressure inside from the gas.
That pressure, exactly. And in fact, nitrogen, this is one of the biggest concerns with nitrogen because it's very, very expansive. If I had one container like this full of liquid, we'd have almost 700 full of gas. It expands almost 700 times in size, and that's why ventilation is so important. Because the gas is going to escape, question is from where? So unfortunately, can't bring it home with you, but I can show you something called the Leidenfrost effect. Now, if I had some leaves, I could show you what happened, put your hand inside of it. Unfortunately, I do not, but what I can demonstrate is something called the Leidenfrost effect. And this is why if it were to come in contact with our skin of it, that is liquid nitrogen. Just, my friend, keep your hands where they are, of course. But you see, it's liquid nitrogen, and it's boiling right now. If you want to blow on it, you can. It's going to add more heat to it. But also notice, please do keep your hands where you are. As I pour it on the tray here, notice how it behaves.
It's like hydrophobic.
Well, not to say hydrophobic, but it is a frictionless surface, because as soon as it comes in contact with the skin or the table here, it boils, and that gas that comes off of it is a gaseous barrier underneath the liquid, so there really is no liquid touching, it's that gas coming off as it boils. So that frictionless environment, and that's why if we were to touch it with our skin, it would boil off, and that gaseous barrier will keep it from burning us as long as it stays in motion. I will say that. It definitely can be very dangerous. And that's the Leidenfrost effect, that gaseous barrier. You can also see it when you're cooking on a wok, for example, a skillet, a very hot wok, you put water on it, and that water starts to dance. That's the Leidenfrost effect, that gaseous barrier underneath it as well. But that's why if it were to touch us, at the end of the world, but if you give me one moment.
That's really cool. It's really cold.
Really cool, huh?
You got a leaf.
All right, AJ, check it out. Here we have organic matter just like us. Now, AJ, are you left-handed or right-handed?
Right-handed.
Right-handed? Got a right-hand glove here for you. Because we can't, our body, call it 75% water. So AJ, I'm gonna submerge it for only a few seconds, 1, 2, and 3. Once I bring it back out, use your right hand with the glove, go ahead and crush it. You ready? All right, my friend, after only 1, 2, and 3 seconds, our leaves in liquid nitrogen, let's see what would happen. Oh, that sounded like glass, didn't it?
Yeah.
Now,
How cold
that's
are
why,
these?
you can touch these. That's the thing, they warm up almost immediately in the air around us, but that's why those leather gloves are so important, because hand confetti, not so cool, but leaf confetti is kind of cool.
I kind of want to keep one of these. This is kind of cool.